Everyone. I want to sort of introduce myself. I'm Dr. Satterfield. I'll be your instructor for this term, and we've got some new hardware requirements this term. I just finished teaching this course back in uh, December, right before Christmas, and it sort of was a surprise to me that suddenly um, the hardware changed. I just happened to spot it in the syllabus. And so I do not have my new hardware yet, uh, but hopefully you do. And if not, don't worry, you'll get it by the end of the week, I'm sure. And then I'll give you a chance to get caught up. Meanwhile, there's plenty of work to do, plenty of reading, getting familiar with the Z books. Now, one thing about the Z book, there are some quizzes, what appear to be quizzes in there, but they're not there to evaluate you on what you've read. They're there as an additional way to teach you. So if you get a question wrong on a ZBook quiz, please go ahead and read the feedback and then select the correct answer. Uh, by the end of the reading, you should have 100% of the correct answers. That's the goal. This is there for your benefit, not to evaluate you to make sure you're doing your reading. Because if if you get through there and you read the feedback and you get all the correct answers marked, you will have accomplished what you need to do. Uh, but the reason it's important, another reason that it's important to go ahead and mark the correct answer so that when you finish, you've got 100% of the correct answers marked, is that uh, even though they're not there to evaluate you, those Z-Book readings uh, show up in the grades. And so if you don't do them, of course, that's going to count against you. But even if you do them and you leave some of the questions marked with the incorrect answer, um, it's going to show up as a less than 100% for that assignment for that week, and that factors into your final grade. So please don't do that. Go ahead and do the readings. If you get the wrong answer initially, read the feedback and select the correct answer and move on. Um, anyway, just quickly again about the uh, new hardware. We're last term we were using a where is it? Anyway, it was a board like this, a Texas Instruments uh, CC3320S Launchpad, and it was pretty good, pretty much fun to work with, and we were using embedded C to program it with, and then so we would write the embedded C code on our desktop, and then using Code Composer Studio, and then we would flash it onto the board and run it, and using UART. Now let's see. I'm going to be talking about these terms a little bit. UART, Universal Asynchronous Receiver Transmitter Protocol. Um, Using that, we were writing uh, status information back to our computer, the one we wrote the program on and flashed it onto the board with, and then so that we could display it in the terminal window and you could see what was going on. So that and the use of the LEDs to indicate what the program was doing. That's how we could tell if our program was successful. So you're going to be doing the same projects in this course. The difference is, and they've been rewritten, of course, because now you're not going to be using this board. You're going to be using the Raspberry Pi with several. Now, this board had everything built into it: temperature sensor, LEDs, all of those things. The Raspberry Pi, they've got you accumulating a lot of peripherals, such as LEDs and a external peripheral temperature sensor. Now, even on this board, they were regarded as peripherals, so we had to use UART, I2C, Inter-Integrated Circuit Protocol, and GPIO, General Purpose Input Output. Now, we had to use all of that to control and or read these peripherals, such as the temperature sensor, the LEDs. So none of that will have changed. The difference is you're going to be using Python, which is the preferred language of the Raspberry Pi. It just works better if you're using all of the peripherals and such. And I sent you a video of a very good instructor showing you how to get started with Python on the Raspberry Pi. But what I wanted to do right now is just, I think this will be helpful for you because you're going to need to review the final project. That's sort of a non-graded task for this first module. You're supposed to review the final project just so it gives you a big picture view of what you're going to be doing. So what I want to do is show you how we accomplished the final project using this board and using embedded C, because the logic shouldn't be that much different. It's pretty much a difference of syntax, and then there may be some other differences. Now, as I said, I don't have my new hardware yet. This sort of came out of the blue. I'm sort of happy about it, though. It's going to be a lot of fun to work with the Raspberry Pi again. I admit it's been a few years, but I'm extremely familiar with Python and all these protocols. So as soon as I get it, I'll be up to speed in 24 hours, and I'll be able to pass that expertise on to you. So not to worry. So anyway, let's go ahead and take a look at the state of that final project, the way that was done using the old language and the old hardware. And what you see here is the report. It's rolling up every second, as was required last term for the final project. Now, I believe you're going to be doing it every half second, every 500 milliseconds. Also, another difference is these temperatures here. This is the, I don't know if you noticed, it just went from, see, when I picked up the board, because the temperature sensor is on the board, and I'm putting my thumb over the temperature sensor now, the temperature, went up quite a bit. I just had supper. I must be warm. So anyway, notice the 0 here in the third position in the status report. That indicates the heat is off. So on the left-hand side, we have and you're going to be doing something very similar. Left-hand side, we have the ambient temperature that we're reading from the temperature sensor. In the second position of this comma-separated values list, we have the set point. And in the third position, we have the heat on or off status. So 0 is off, 1 is on. And then finally, on the end, we have the number of seconds since we started the thermostat. So you're going to have all of this plus one more. You're going to need to, you see the way this works, I've got a button I can press here and increase my set point. I just clicked a button on here. And notice we have a red LED on now. And we're displaying a 1 up here for the state of the heater. Now, so if we move the set point back down so that it's even with the ambient temperature, the set point is even with the ambient temperature, so the heat goes off. We have a 0 here. Our red LED is no longer on. It's off. Now the thing you're going to be doing additionally, because you have an extra LED to work with, you not only have a red LED for the heat, but a blue LED that you can use to indicate that the air conditioner is on. So in other words, if I lower the set point below the ambient temperature, you don't see the heat come on, obviously, but nothing else happens either. This time, since we have the resources, you're going to show a 1 here in a separate column, and here you're going to turn on a blue LED, which we don't have here, but on your new hardware, you would be turning on a blue LED to show that the cooling system was on, because the ambient temperature is now greater than the desired set point. So that's the requirement. It sounds simple, and it's really quite a bit of fun. But now regarding the logic, again, as I said, this is going to be very similar, I believe. You're going to be using all the same things, all the same players, timer, interrupts for when you press the button to increase or decrease the set point. That's all here. And then you're going to be using UART to output the status at regular intervals. And you're going to use the timer to keep up with those intervals. And you're going to be using GPIO, general purpose input output, to change the state on or off of high or low of the LED. And that sort of thing. So let's take a look first at the main loop. Now, when I implemented this, I encapsulated a lot of functionality into sort of separate methods that I could call so that it keeps the main thread. This is your task scheduler. This main thread, this everlasting loop here is your task scheduler. And so I didn't want to junk up the main thread method with all of the things that I have written into these methods that I'm calling, because then it becomes very difficult to see the real meat of the thing, which is the task scheduler. So here we have a local variable called timer, initializing it to 0. And then, so when you start up, when you flash this, because you won't be flashing onto your board, we're going to be programming directly on the device with Python. But here we flashed the program onto this board, and so as soon as you do that and it starts running, and it comes here and it initializes the system, sets the temperature state, which is the 1 or 0 for the heat being on, to off, displays starting task scheduler, initializes the timer, and then enters this endless loop here. So this is until you stop, pull the USB connection out of your desktop computer to kill the program, it's going to continue looping. As you can see here, it's been 1,414 seconds and so forth. So inside this loop, now first let's take a quick look at init timer. But I can just explain it, and then we'll look at it later. But in init timer, well, let's take a look. We have first of all, we have some constants here, and that's always a best practice. If you just start putting these numbers in place, like the 2, the 5, the 10, the 100,000, that's what we call magic numbers. Somebody who has to maintain your code later on isn't going to know probably what that number represents. And so if there's a problem, that increases the risk that that person might think, oh, well, maybe it's this number, and then change it, and then you go down that rabbit hole. So it's best to put things in well-labeled constants, and then use those constants everywhere. On top of that, if you need to use the same value in multiple places, then you use the same constant in all those places, and then if it needs to change, you only need to come here. You don't have to go looking for everywhere where you've used 100,000, because there might be another place where you used it for some entirely different purpose, not to represent a 100 millisecond cycle. But anyway, now in the old, and I'll show you why I used 100 millisecond cycles. In the original project last term, we were required to check the state of the buttons, check to see if those interrupts, the button, we assigned a callback to 2 buttons, one to increment the set, excuse me, set point desired temperature, and another one to decrease the desired set point. So every 200 milliseconds, we were required to check to see if either of those buttons had been pressed. And if they had, then we increased or decreased the set point as appropriate. So as you can see, this button check modulus is 2. And so the reason for that is because the timer value, and I put it on a comment here so I could show you, because the timer value is incremented every 100 milliseconds. You see, every time through the loop, through this eternal loop, we're incrementing the local timer variable by 1. So the second time through the loop, this is going to equal 2. And so 2 being, this is modulo arithmetic. So what this means is if this timer value, which would be 2 the second time around, is if the remainder after you divide it by 2 is 0, meaning it's evenly divisible by 2. So if it's evenly divisible by 2, then we're going to check the set point buttons and increment or decrease, if necessary, the set point. So every 200 milliseconds, since these are 100 millisecond cycles, every 200 milliseconds, this is going to be true. And the same thing for this one. I don't think you have either of these timing requirements, but you do have the report timing. So this was, if it's evenly divisible by 10, so that meant every second. So if you're cycling through this loop every 100 milliseconds and incrementing your timer variable by 1 each time, then every 10th time through, the value of timer is going to be evenly divisible by 10. And so that tells us that it has been 1 second since this was true. And so we send the message to the UART, and then we increment our seconds variable. Well, seconds is not a local variable because we're going to need to read it, excuse me, up in the send state to UART. Excuse me, I've been suffering from a cold all winter, it seems like. So let's take a look at some of these. And again, you can see how clean this looks. Excuse me, if you encapsulate specific functionality in its own method that you can call from a different method, and then you can keep the calling method clean so that it's easy to see exactly what it's doing. If you had all of this code from here and then from here and here, if all of this was just loose inside the task scheduler, it would be very difficult to follow, making it very difficult to debug and to maintain. So this is a best practice. So let's take a look at Well, I promised you first we were going to take a look at init timer. So let's take a look at that. And if I'm not mistaken, I think you'll be getting a lot of this in your starter code. So the main thing to remember, the period, you want to set it to that 100 millisecond cycle, the 100,000. The reason it's 100,000, of course, is this board works with microseconds. So you need 100,000 of those to be 10 milliseconds. 100 milliseconds. And then, so you want to use this for the period, this 100 milliseconds. And then you want the timer mode to be continuous callback. Now, it may be different on the, with those protocols on the Raspberry Pi, we'll see. But basically, same principle. It's going to be the same principle. And then timer 0. Now notice timer 0 is not a local variable in here. The timer 0, I believe, is a handle to the timer. So you want to put that up at make that up at the class level. And where is it? Here it is. Timer handle timer 0. So we can access this in any method in the program. Now this set timer period, I'm not actually using that. A lot of this code in the final project we brought forward from the first two projects. And I believe set timer period, we were using that for probably what you're going to be doing next week for the pulse width modulation. So when that time comes, by then I'll have my my hardware, and I'll be able to show you how to do it the way we're doing things now. But it's kind of hard to do that when you don't have the hardware yet. And send state to UART. That's simply a display using a formatted string. Now, as I said, you're gonna need to just use pretty much the same thing, and then include one more value here, also a %D, to represent whether or not the cooling system is on or off. Read temp. I believe you'll be getting this pretty much in its entirety in the starting code. Init I2C, I believe that's starter code. Init UART, same thing. So don't worry too much about these just now. You want to end up the course understanding all of this, but we're not going to make you sweat too much. But the main thing is to understand the logic and how you would put all these things together, and then do something creative, with a set of requirements. Um, that's what you need to come out of this with the ability to do. So here we are again with the knit timer. And again, the things to remember here are the period and the timer mode, continuous callback. And then here are the callbacks. Let's see, where's the timer callback? Now the timer callback is very simple. All it's going to do is set the timer flag to 1. Now the timer flag, let's take a look here. The timer flag is 0 while the timer is in operation. As soon as it becomes 1, we've reached the end of that 100 millisecond cycle, and we can do whatever we need to do at that point, and then the timer restarts. But this is a callback for one of the buttons, and I don't remember which is which. One of them, when this button flag is 1, means this is an interrupt has fired. So that means the button was pressed. As soon as it's pressed, it comes here, sets the flag to 1. And so when button 0 flag is 1, we do something a little different than we do if button 1 flag is 1. And let's see which is which. Excuse me. So here in the check set point buttons, if button 1 flag is 1, then we increment the set point by 1. If button, and then we reset button 1 flag to 0, because otherwise, then every time subsequently when we came here and checked, this would always be 1. So as soon as you do whatever you need to do because it's 1, then you go ahead and set it back to 0. Same thing with button 0 flag. With button 0 flag, we were decreasing the set point. And in your final project, the thermostat project, you'll be doing all of this same stuff, just with a different set of hardware and a different language and different syntax, but same logic. And then here, compare ambient to desired temperature. So in this method, I encapsulated a call to read temp, and I believe everything in read temp you'll be given in the starter code. So we read temp into the ambient temperature variable, and then we simply check here if the ambient temperature is less than set point. Then we need to turn on the heat, because we've, if the ambient temperature is 22 and our set point is 23, then the user wants the ambient temperature to be 23, so we need to turn the heat on. Else, and here you'll need more than just an if-else, because you've got 3 states to be concerned with here. In this project, if it was less than, then we turned the heat on. If it was the same as or greater than, then we didn't do anything except turn the heat off. What you'll be doing is checking, okay, if its ambient temperature is less than the set point, we turn the heat on. If it's um, greater than, um, then we turn the cooling system on. Else, and there'll be some extra logic here, but so in other words, if it matches exactly, then we don't want either the heat or the cooling system on. And now, of course, you don't want both on ever. Um, so we'll talk more about that later on. But um, so then at the bottom of your eternal loop here, you just wait for the timer flag to be 1 again, and then you immediately set it back to 0, increment your timer variable, and then just go back up to the top of the loop and start checking your modulo arithmetic to see what you need to do, what it's time to do. So anyway, I'm gonna wrap up before this cold takes over. The nighttime, it's late at night, and it's worse at this time of day. So anyway, I just wanted to get out in front of you a little bit, introduce myself, show you some of the logic you'll be working with on your final project, even though unfortunately I can't yet show you how to do it in your new environment. But I'm sure I'll have my hardware by midweek, and then by the weekend I'll be ready to put together some nice videos for you. So enjoy the week, relax, and get familiar with everything. And I think you might have a quiz. I'm not sure if that's this week or next, but now remember too on the quizzes. Now I'm not talking about the Z-Book quizzes. Those, remember, always 100%. Just go ahead and figure out the right answer from the feedback and check it if you missed it. But on the other quizzes, I think you get 2 attempts. So definitely take, unless you get 100% the first time, definitely take it again. Take note of what you missed, and go look up the answers if the feedback's not sufficient, and then try it again. And if you feel like you got the right answer and there's just something wrong, I tell you honestly, there's a quiz up in it might be module 7 that unless it's been fixed, even if you could get exactly the right answer, and it would just mark it wrong, So I just had to go in and give everybody 100% on that one. If you took it at all, and then I would get, of course, if someone got actual wrong answers here or there. Most people got plausible answers throughout on that quiz, but if somebody didn't, then I would just give them enough feedback so that they would understand their mistake. But on that one, I just felt like the auto scoring algorithm was so flawed on that quiz, and after all the trauma of experiencing that, I figured everybody who took it deserved 100%, and so that's just who I am. So enjoy the week, and I'll see you next week with hopefully we'll be rolling on the new hardware. Good night.